So this video is from Chapter 5 in the Chemistry 2045 textbook. I took some of the content from Chapter 4 and I blended it in with Chapter 5. The end of Chapter 4 in the book talks about a few different reaction types. I decided to put all the chemical reaction types together into one single chapter, so I moved them to everything into Chapter 5. So I'm calling Chapter 5 Introduction to Solutions and Chemical Reactions. Most of the chemical reactions we're going to be dealing with are in solution phase. You've got, acid-base reactions, single replacement reactions, decomposition reactions, usually involve some sort of solution. When it comes to a solution, they're a homogeneous mixture, meaning they're uniform throughout. Homogeneous mixture involves a solvent and a solute. Now you can find all this again in my Chemistry 1025 videos, Module 10. So the solvent is usually water. It's a substance which is in a higher amount, and the solute is what is being dissolved. So that could be table salt or sucrose or some particular acid. It could be oxygen and air. Air is mostly nitrogen, so the oxygen is a smaller amount, so you can think of the oxygen as being a solute. In any event, you put this all together, we get a solution. So we're primarily going to work with aqueous solutions, meaning water-based. When it comes to a solution, we get to be able to measure what's known as concentration. Concentration deals with how much solute is dissolved in a given amount of solution. The different concentration units, the one we're going to focus on in this class is molarity for the most part. Molarity, as you may recall from 1025, is capital M. It means molarity is moles of solute over liters of solution. Not liters of water. Okay, it's the total volume of the solution in liters. So here's examples. Concentrated solution simply has more solute particles dissolved. Dilute solution got less solute particles. So imagine food dye. It might be really, really red. Add some more water to it. You dilute it down. Now it turns kind of pink. You go from a concentrated solution to a more dilute solution. And here's my definition for molarity. Moles of solute per liter of solution. And we use capital M for this. Now, we could say, for example, a solution is 2.5 molar. You may see that. Or you might get 2.5 capital M. Capital M means molar. Or you might see 2.5 moles per liter. So all these three expressions all mean the same thing, talking about a 2.5 molar solution. This is written out in different ways. As far as how you make a solution, it's customary we use what's called a volumetric flask. A volumetric flask has got one line written on it. It's one line up here where we're going to fill the solution to, usually water. So for example, if this is a 1 liter solution, this line right here, where the meniscus would be exactly 1.00 liters. If it was 25 milliliters, it would say 25 milliliters. If it was 500 milliliters, it would say 500 milliliters, whatever. But it's only one line. We add the solute, in this case it's sodium chloride, add the powder to the flask. We're going to add some water to it, maybe right below the neck. You want to leave some airspace so you can swirl this. You swirl, swirl, swirl until it's all dissolved. And then you're going to fill the liquid to the meniscus. You put a cork on or a stopper, and you would just invert it up and down several times to make everything all nice and uniform. So this is a common way of making a solution. So we can express this as 0.5. So if it's a 0.5 molar solution, it'd be 0.500 moles per liter. Or we can think of this as being 1 liter over 0.500 moles. We will use this as a conversion factor in calculations. Let's take a look at these problems. And let me delete this part down here. So for example, what is the molarity of a sodium chloride solution if 5.00 grams of sodium chloride is dissolved in water to produce a 250 milliliter solution? So you say, well, 5.00 grams of NaCl. We get to convert grams to moles. So 1 mole of NaCl. Now we have to find the molecular weight of this. Sodium is 22.99, so 22.99 plus 35.45, that's the atomic weight for chlorine. You get 58.44 grams. So now notice grams of sodium chloride cancel out, leaving us with moles of sodium chloride. Now molarity is defined as moles per liter. We have 250 milliliters, so the way I do the problems, I'm just going to hit 1 over 250.00 milliliters. So now if you got moles per milliliter, we'll get rid of milliliters, say, well, it's 1,000 milliliters in 1 liter, and now the milliliters all cancel out, and what we end up with is moles in the top, liters in the bottom, and that is the definition of moles per liter. That is molarity. So 5 divided by 58.44 equals, divide that by 250, and then multiply that by 1,000. And you should make sure you can verify these calculations. But I got 0.342 molar NaCl. Or you can express this as moles per liter, or you could just say molar. Any of them would be acceptable. In this particular problem here for sig figs, 5.00's got 3 sig figs. 250.00's got 5 sig figs. So we always go by the smallest, so I need 3 sig figs. That's how we solve that problem. The next one, how many grams of sodium bromide needed to prepare 100 milliliters of 0.75 molar solution? So recall the molarity is equal to moles per liter. So if you multiply both sides by liters, you get molarity times liters gives us moles. Now the way we see this is that, remember, molarity, capital M, means moles per liter. Multiply that by liters, again that's what capital M stands for. Notice liters cancel out, that gives us moles. So that's what we need to do. We're going to multiply volume times the molarity to get moles, then use the molecular weight of sodium bromide to find the number of grams. Alright, so 100.00 milliliters of NaBr solution. Now we know molarity is moles per liter, and I've got milliliters, so that's a problem. So, oops, I have to get rid of milliliters. Well, 1 liter is 1,000 milliliters. So if milliliters can't be divided by 1,000 to convert the milliliters to liters. Now we multiply that by the molarity. That is 0.75 moles of NaBr per liter. That's what capital M means. Notice now how liters cancel. Now I got moles. We multiply this by the molecular weight of sodium bromide. That will give us the mass in grams. So sodium is 22.99. Check your periodic table. Bromine is 79.90. Add these up, will get us the molecular weight of sodium bromide. 22.99 plus 79.9, and that is 102.89 grams. So notice now moles sodium bromide cancel, leaving us with the units we want, which are grams of NaBr. Check sig figs. We have 100.00 and 0.75. 0.75 has got 2 sig figs, so our answer is going to get 2 sig figs when we're done. 100 divided by 1,000 times 0.75 times 102.89 equals, and you get 7.7 grams NaBr. BR. And that's how we solve that one. So this is how I do the problems. Alright, as far as dilutions are concerned, this is called the dilution formula. This might be new from Intro to Chem. It says molarity 1 times volume 1 equals molarity 2 times volume 2. Sometimes this expression is shown as C1 V1 equals C2 V2, where C just means concentration. So in the case you're working with maybe a different concentration unit, like parts per million or molality or weight percent or some other whatever, C just means a general concentration unit. I'm using M here for molarity because that's what your author of your textbook uses, but it doesn't make any difference. The 1s represent the original concentration, the original volume, and the 2s represent the final, like after diluted. So the way this works, let's say we have 10 molar solution, stock solution, and we have 150 milliliters, or 0.150 milliliters, whatever. We want to dilute this to 3 liters total. I want to make a 3-liter solution. What is going to be the new molarity? Well, we use M1V1 equals M2V2. Our M1, that's the original molarity, 10.0 molar. The volume I'm diluting is 150 milliliters, or 0.150 liters. My new volume is going to be 3,000, or 3 liters. 3,000 milliliters, or 3 liters. And our job now is to find M2, that we don't know. So 10 times 0.150 divided by 3. And then that should give us, let's see, you want to find the new molarity. So M2 equals 10.0 molar times 0.150 liters divided by 3.0 liters. That will give us a molarity of what? See, so 10 times 0.15, divide that by 3, and we get 0.5. 0.50, need 2 sig figs, molar. That'll be the new molarity. So if you do this dilution here, how about this one? Calculate the molarity of a solution prepared by pouring 25 milliliters of 2.50 molar NaCl solution into a 500 milliliter flask and diluting to the fill line, meeting to the meniscus. Well, M1 V1 equals M2 V2. So we start with this, that's the 1s, and we're making this. There's the 2s. There's the 1s, and there's the 2s. So molarity 1 is 2.50 molar. Volume 1 is 25.00 milliliters. Molarity 2 we don't know. V2 is 500.00 milliliters. Now the prior example, I use liters for volume. This is milliliters for volume. It doesn't make any difference because milliliters are going to cancel it anyways. All that's left over is going to be molarity. So M2 equals 2.5 molar, 250.00, oopsies, 25 rather. .25 milliliters. Now we'll just divide that by 500. 500.00 milliliters. So notice milliliters cancel out, giving it just molar. So 2.5 times 25, divide that by 500. Check sig figs. 4 sig figs, 3 sig figs, 5 sig figs. Go by the smallest, which is 3 sig figs. So 0.125 molar solution. Next one, how many milliliters of 1.75 molar HCl needed to prepare, that's the change, 100 milliliter solution of 0.75 molar. So I'm starting off with this concentrated solution, M1, we know that. That's the 1.75. V1 we don't know, because that's how much we're taking out. So we're going to get 1.75 molar solution. V1 we don't know. We're preparing a 0.75 molar solution. Total volume of 100.00 milliliters. That was just basic algebra before. We'll solve for V1. It'll be milliliters. V1 equals 0.75 molar times 100.00 milliliters. Divide that by 1.75 molar. V1, and that'll tell us the answer to that. 0.75 times 100. Divide that by 1.75. And we get 42. Now to check sig figs, I need 2 sig figs. So actually 43 milliliters. So I take 43 milliliters of the original solution, put that into a 100 milliliter flask, and then filled to the mark, mixed it, you would now have a 0.75 molar solution. This is what's commonly done in the lab when you make acid solutions. You buy a large bottle from the manufacturer. It might be 10 molar acid. We take a little bit of that out, put that into the flask we want to dilute it down to, and then we prepare solutions for the lab. Alright, when it comes to stoichiometry, we have to use our balanced chemical equations. Again, you can find this in Module 10 from Chem 1025. So here's a balanced equation. We can now use molarity as a conversion factor. So this example of an acid-base reaction, you want to calculate the molarity of the sodium hydroxide. 10.00 milliliters of 2.50 molar HCl reacts with 13.75 milliliters of calcium hydroxide. This is basically an example of a neutralization reaction or a titration question. So, what's our A, what's our B? Our A has all the numbers, our B has the question mark. So calculate the molarity of calcium hydroxide, that's going to be our B. We don't know the molarity. I always start with the volume of the acid, the volume of what we know. So we know the volume of the acid, 10.00 milliliters of 2.50 molar HCl. So this 10.00, this is the volume of the acid. 10.00 milliliters of HCl. Now molarity is moles per liter. So I say, well, 1 liter is 1,000 milliliters. That makes the milliliters cancel out. That's 2.50 moles per liter. So it's 2.50 moles per 1 liter of HCl. So now liters cancel. Now we either use a mole ratio. It's always B over A. Look at the balanced chemical equation. For every 1 mole of calcium hydroxide requires 2 moles of HCl. That came from the balanced equation. It's always B over A. So now moles cancel out. Our job is to find the molarity. Recall molarity is moles over liters. And we have 13.75 milliliters. So now I'm going to divide this by the volume of our calcium hydroxide, 13.75 milliliters. That's 1 over 13.75 milliliters. And now we'll convert milliliters back to liters to get the proper units. 1,000 milliliters is a 1 liter. So now we'll cancel out milliliters to get liters. So now what we have is moles on top and liters on the bottom. That is the definition of molarity. This is what you have to do. So your calculator is going to be 10. Now the thousands also cancel out. 1,000 at the bottom, 1,000 on the top, they're going to cancel out. So it's going to be 10 times 2.5 divided by 2 divided by 13.75. And that gives us, now check sig figs. We need 3 sig figs. That number 2.50 has got the fewest number of sig figs. So 0.909 molar CaOH, parentheses twice, calcium hydroxide. That is the molarity of that solution. The next one, same chemical reaction. A 15.00 milliliters of 2.50 molar HCl reacts with 20.00 milliliters of 1.75 molar calcium hydroxide. How many grams of calcium chloride can you produce, theoretically? So this is a limiting reagent stoichiometry problem. I'm mixing these two solutions together, this acid and this base together. We're producing calcium chloride. The question is, how much can you make? Does the acid run out first, or does the base run out first? Well, we have two A's and a common B. HCl is A1, calcium hydroxide is A2, my B is going to be calcium chloride. Well, let's calculate that. We'll start with HCl. 15.00 milliliters HCl, which is 1,000 milliliters in a liter. That cancels out milliliters. And now we need to multiply this by the molarity of HCl, 2.50. Per liter of HCl. That makes liters cancel out. Now you have moles of HCl. Now we use the mole ratio. It's always B over A. So the number in front of calcium chloride is a 1. 1 mole CaCl2 over 2 moles HCl. Now, what are we looking for in this problem? We're looking for mass in grams, which means I now need the molecular weight of calcium chloride. So calcium has an atomic weight of 40.08 grams per mole. Chlorine is 35.45, so 35.45, but I have to double that, so times 2. That's going to be 70.90. So 70.90 plus 40.08, that is 110.98. So we have to multiply by the molecular weight. Do the math and see what we get. So 15 divided by 1,000, notice 1,000 does not cancel in this example, times 2.5 divided by 2 times 110.98 equals 2.08 grams CaCl2. So that is one possible answer. So we'll repeat this again now with their calcium hydroxide. Well, we have 20 milliliters of that. Exact same steps. 1,000 milliliters in a liter. Multiply by the molarity. 1.75 moles of calcium hydroxide per liter. Milliliters cancel. Liters cancel. Now here the mole ratio is going to be a little different. You can notice a number in front, there's a 1 in front of calcium hydroxide and 1 in front of the calcium chloride. So it's 1 over 1. Oops. So moles cancel here. And last but not least, we multiply by the 110.98, convert to grams. See what we get this time. 20 divided by 1,000 times 1.75 times 110.98, that gives us 3.88. Okay, so now we have two answers. But remember, we always pick the smaller one of the two. So we can't make any more than 2.08 grams calcium chloride because that is the smaller amount. Therefore, HCl is the limiting reagent. HCl is a limiting reagent in this case. So that's how we do basically solution stoichiometry. For more examples of these, please take a look at my Module 10 videos from Chem 1025. As far as making solutions, if the solute and solvent have similar what are called intermolecular forces, they will tend to mix together and make a solution. If their intermolecular forces are dissimilar, they will tend not to make a solution. We'll cover that in much more detail later in this course, one of the last topics we're ever going to cover in 2045. The idea here is that if the solute-solvent interactions are sufficient or strong enough, we can basically break up the solute interactions and make the solution form. Okay, so basically we want the green particles to interact strongly with the purple particles. That will then make a solution. If the purple particles interact so strongly that the green ones can't separate this, we're not going to make a solution. So that's the whole idea here. So depending on what the solute and solvent are, some solutions will form and some solutions will not form. This example of water. Water is an example of a polar molecule. You'll see diagrams like this or representations like this later in the course as well. This delta minus means this part of the molecule's got negative charge. These delta pluses means that part of the molecule's got positive charge. This is the case of water. Water is with two H's. It's a bent molecule, meaning these H's are not linear across. So the oxygen is more electronegative than the hydrogen, so therefore the oxygen part of the molecule is negative and the hydrogen part of the molecule is positive. Water will tend to dissolve other molecules which have a similar behavior, or it will tend to dissolve many different ionic compounds because it's plus-minus interaction here that can break up a positive-negative charges in an ionic compound. So in the case of sodium chloride, the negative part of the water molecule can interact strongly with the sodium because that's positive. The oxygen part of the the hydrogen part of the water molecule connect strongly with the chloride ions because that part is negative. So we have opposite attractions. The water interactions with the sodium and the water interactions with the chlorine are strong enough to break up the sodium chloride interactions themselves. So basically what happens is that these water molecules begin to surround the sodiums and the chlorides and cause it to dissolve. This will occur until the solution becomes saturated such that the water can simply not dissolve any more sodium chloride. When this occurs, we can make a solution which is can conduct electricity, because now we have positive and negative ions floating around in solution surrounded by water. So if you add table salt to a beaker, plug like a basic light bulb tester with electrodes into the solution. If you hook up to a power source like a battery or electrical outlet, if current can be conducted through between the electrodes in the solution, we get what's called an electrolyte. And the light bulb is really bright, you get what's called a strong electrolyte, meaning we have lots and lots of ions in solution. Sugar does not produce any ions. Sugar, for example, like glucose, is C6H12O6. When this dissolves, you do not make any ions, so that's solid. When you dissolve it, we just get C6H12O6 aqueous, and no ions are formed. Versus table salt, you get Na plus aqueous and Cl minus aqueous. We get these ions, which causes electricity to be conducted. So an electrolyte will conduct electricity. A non-electrolyte will not conduct electricity. Now we do have this intermediate case called weak electrolytes, such as acetic acid. Acetic acid looks like this. It's HC2H3O2. And when this ionizes, we get H plus and C2H3O2 negative. These are aqueous. However, these ions here are very few. So very few ions. So maybe it's actually less than like 1%. Less than the 1% of this acetic acid actually forms these ions. Over 99% of it stays in the combined form, where there's no ions here at all. So if you get very few ions, it's called a weak electrolyte. We'll study this idea in much more detail in Chemistry 2046. So for you guys in this class, predicting whether something is weak is going to be quite difficult, because how do you really know for sure which ones break up strongly or not? I will tell you if it's a water-soluble salt, like sodium chloride or sodium bromide or things like that nature, it will be strong. If it doesn't have any ions at all, like it's molecular, like some kind of molecular solid of some sort, it's not going to make any ions, and that will be a non-electrolyte. So sugar is an example for that. Okay. So acids ionize in water to make H plus Cl minus. Okay. Strong acids do this a lot. Weak acids will ionize only a little bit. So it turns out most acids are weak. There's actually very few strong acids. Strong ones are going to be HCl, HBr, HI, H2SO4, HClO4, and HClO3. That's basically the list of strong acids. Pretty much every other acid you can think of, they're going to be weak. That actually encompasses most acids. There's actually very few strong ones. I'm not going to ask you in the test which ones are strong, which ones are weak, but I want to understand that most acids are actually indeed weak. The ones you find in group 7 in the periodic table, HCl, HBr, HI, they're good examples of strong acids. Oh, nitric acid as well. HNO3 is also on that list. When something dissolves, it breaks up into its ions. So sodium sulfate, when this breaks up, notice we have 2 sodiums. This you should be able to do. 2 Na plus SO4 minus. This came from the polyatomic ion chart, the sulfate. Sodium sulfide, again, 2 sodium, so you get a 2 in front here, with just 1 sulfide. In the case of these acids here, H2SO4, both of these acids can be ionized to make 2H plus and SO4 negative 2. So you should be able to predict what kind of ions you can expect to form. Try something with a base, for example. extra space here. Alright, it's not letting me edit that for some reason. But how about something like this? Something like magnesium hydroxide. You put that in solution, you can get Mg, the positive 2 charge, plus 2OH minus. Okay, so as long as you pay attention to the subscripts, you can predict what you're going to form. Some salts are water soluble, some salts are not water soluble. So silver nitrate will dissolve in water, silver chloride does not dissolve in water. It's called insoluble. This is some solubility rules. You need to know this. I'm not going to provide you a solubility chart on the test. So you need to basically memorize this page and this page. Okay. So things like a good hint: all alkali metals dissolve in water. This is group 1. Anything in group 1 will dissolve. All nitrates, all acetates dissolve. Okay. So there's no exceptions here. Most group 7 ions dissolve. That's group 7. So most of them all dissolve with the exception of silver and mercury and lead. Okay. So what you may want to do is memorize some of the exceptions. So you can think about it that way. Again, most sulfates dissolve. Again, with the same exceptions. Again, we got we got lead, we got silver, and we also got strontium, barium, and calcium. Okay, so you need to basically figure out a way to memorize this chart. Most hydroxides do not dissolve. Most sulfides do not dissolve. Most carbonates do not dissolve, and most phosphates do not dissolve, with exceptions of the ones on the previous chart. So sodium phosphate will dissolve. Sodium carbonate will dissolve. So that's basically how this chart works. So in Chem 1025, you're given a solubility chart. This class, you're not going to be given a solubility chart. This is important for when it comes to predicting complete ionic equations and net ionic equations.